For the next paper, we have a couple of speakers. One is Bowen Liu, which is a postdoc researcher, and the other is Xinyang Wang, which is a PhD candidate at the Hong Kong University of Science and Technology, advised by Kai Chen. They are both interested and focused on building high-performance programmable and extensible network services for data center application. The floor is yours.
Okay, thank you. Good afternoon, everyone. It's our pleasure to present our work today at SIGCOMM'. I'm Bowen Liu, a postdoc researcher, and this is Xinyang Wang, a PhD candidate, and we are both from Hong Kong University of Science and Technology. The title of our work is CEIO, a cache-efficient network I/O architecture for NIC-CPU data passes. This is joint work with my colleagues led by Professor Kai Chen at HKUST. I would like to begin by introducing why host network I/O is becoming such a bottleneck in data center networking. A typical network flow starts from a remote switch, arrives at the NIC, and is then transferred through the host memory hierarchy, and finally, it proceeds by CPU cores. We refer to this final stretch from the NIC to the CPU as a network I/O system, or more specifically, the last mile of network transmission inside the host. This I/O system was not seen as a bottleneck traditionally, but today, maybe that assumption no longer holds. We think the data center network has entered a new era of imbalance. Network devices such as NICs and switches continue to scale rapidly in bandwidth, now reaching 100 to 400 Gbps and beyond. In contrast, the intra-host hardware, such as CPU frequency, cache size, and memory bandwidth, has stagnated due to the slowing of Moore's law. The development gap pushes the host network I/O subsystem to its limit. In other words, the NIC can inject packets at line rate, but the host network I/O cannot always keep up. For example, the I/O speed may be limited by PCIe memory bandwidth or the CPU processing speed. To address this rising pressure on host network I/O, hardware vendors have introduced the two key acceleration techniques, direct data I/O, as known as DDIO, and the remote direct memory access, as known as RDMA. Let me briefly explain what each of them does. DDIO allows the NIC to directly write in incoming packets into the last level cache instead of DRAM. This significantly reduces memory access latency, allowing the CPU to process packets faster. On the other hand, RDMA enables the NIC to transfer data directly to or from host memory without involving the CPU at all. This is because the network stack has been offloaded into RDMA NIC for processing, and then the network transmission can be completed and bypass the CPU. Together, these two technologies enable what we call accelerated I/O flows. We can broadly classify them into two categories. The first one, CPU-involved flows, which rely on DDIO, the data passes NIC, last level cache, and CPU. The second one, CPU bypass flows, enabled by RDMA, the data passes NIC, last level cache, and the DRAM. Although DDIO and RDMA enabled accelerated I/O paths, their performance critically depends on efficient usage of the last level cache. Let's take a closer look at why last level cache inefficiency leads to suboptimal performance, regardless of whether the flow is CPU involved or CPU bypassed. Recall that with DDIO, all incoming I/O data is first written into the last level cache, even for the RDMA flows. However, the last level cache is a limited and shared resource, typically just a few megabits, and is shared by all CPU cores and the NIC. The limited size can cause frequently cache eviction and cache misses, and the shared feature can cause significant competition among different I/O flows. The consequence of inefficient last level cache utilization would force both CPU-involved flows and CPU bypass flows into longer data passes. For example, CPU-involved flows degrade from NIC last level cache CPU to NIC last level cache DRAM and CPU, increasing both latency and CPU load. CPU bypass flows degrade from NIC last level cache DRAM to NIC blocked last level cache and slow DRAM, congesting memory bandwidth and PCIe. Finally, last level cache inefficiency weakens the intended acceleration, causing throughput degradation and higher tail latency, even with DDIO and RDMA enabled. To unleash the potential of these techniques, recent efforts have explored two directions to mitigate last-level cache miss for I/O efficiency. The first one is limiting the I/O upload rate, and the second one is limiting the I/O accessible capacity. Limiting I/O rate, this approach tries to slow down the NIC when the CPU or memory become overloaded. A representative solution here is host congestion control, which uses reactive congestion signals such as I/O buffer occupation or memory pressure to dynamically reduce the NIC's DMA rate. The second one, limiting I/O capacity. This method tries to constrain how much data can be in flight through the system at any time. An example is sharing, which aggregates all received buffers into a fixed size shared ring that is smaller than the last level cache capacity. And then the I/O data will be constrained within last level cache so that avoid the cache misses. While promising, we found they face two fundamental limitations. Reactive control suffers from slow response and fixed buffers risks packet loss, both of which result in suboptimal performance in practice. To demonstrate the impact of these limitations, we conduct experiments under two common data center scenarios, dynamic flow distribution and network burst. We choose two representative workloads, a key-value store based on ERPC built on DPDK, and an in-memory distributed file system named LineFS built upon RDMA. As the figure indicates, both host CC and share ring show partial improvements up to 1.3 times and 1.7 times throughput gains, respectively under static conditions. But under realistic scenarios, such as changing flow ratios or network bursts, their performance drops sharply. Because host CC suffers from unavoidable cache miss, and the share ring suffers from unexpected triggers of congestion control due to the packet loss. This brings us to the core motivation of CEIO. Instead of reacting after congestion or fixing the buffer size regardless of workload dynamically, why not control the I/O rate proactively and buffer excess data elastically at the NIC? This is a key insight that drives our architecture design. And then Xinyang will introduce the detailed design of CEIO.
Okay, thanks, Bowen. And next, I would like to introduce our detailed design, the CEIO, a cache-efficient network I/O architecture for the NIC to the CPU data path. Well, the key question we need to answer in our paper is, what is the sweet spot between the I/O rate limits and I/O capacity limits? We know the system requires faster rate control to reduce the uplink rate when the CPU cores cannot consume I/O traffic in time. We also know the need for a backup mechanism to observe burst while waiting for the rate control to take effect. So we introduced two design components in CEIO. The first is NIC-driven credit-based flow control. When the packet arrives, it must consume a credit before being DMA to the host memory, and the CPU cores would replenish credits when they have processed a batch of packets. And intuitively, the credit-based flow control is both lightweight and effective. Its implementation is simple, causing minimal performance overhead, while ensuring the I/O traffic does not overflow the last level cache, as the total number of credits is bounded by the LLC capacity. And second, we need to handle the scenario where credits are exhausted, which motivates the second design component, the elastic ONNIC and host I/O buffer management. Instead of dropping packets, CEIO stores excess data in the NIC memory. The CPU can then fetch this buffered data on demand, and the elastic buffer manager preserves packet order and mitigates synchronization overhighs. Well, however, there's no free lunch in system-level research, right? This principle also applies to CEIO's design. As you can see, CEIO splits the I/O path into two logical routes. The first path is fast path, from the NIC to the LLC to the CPU and the RAM, enabled when the credits are available. And the second is slow path, from the NIC to the ONNIC memory and accessed by the CPU on demand, used only when the LLC is full. This architecture split gives rise to two technical challenges. First, how to mitigate the high latency of the slow path, especially for the CPU-involved flows. And second, how to minimize the interaction overhead, such as the reordering and blocking that occur when CPU cross-access packets from the ONNIC memory. And the rest of our design tackle these two challenges directly. Okay, here is the first design, and credit-based flow control. Recall that once the LLC is full, for example, no more credits, the flow is temporarily moved to the slow path, and packets are buffered on the NIC. And the slow path certainly introduces extra latency since CPU need to access the ONNIC memory, which is typically slower than accessing the host memory hierarchy. So to mitigate the latency penalty of slow path, we give the CPU-involved flows higher priority because the destination of the CPU-involved flows are CPU, which is more sensitive to the LLC usage. And we achieve this by using a lazy credit release mechanism. Credits are only released after a batch of packets is processed, which naturally favors CPU-involved flows that drain buffers fast. As a result, CPU-involved flows are more likely to stay on the fast path, while the CPU bypass flows, which are slower and often bulk transfers, tend to fall back to the slow path. Okay. Now let's look at the second core design of CEIO, the elastic buffering, which reduces the interaction overheads of the slow path. Recall that when a flow runs out of the credits, its packets are temporarily buffered in the ONNIC memory, forming the slow path. Then a network flow would be split. Some packets located in the fast path and some in the slow path, right? To handle this, CEIO introduces a software ring that sits above both the fast and the slow path rings. This software ring has two producer, one consumer structure. And fortunately, we find each low-level ring can preserve order itself. Then we let CEIO enforce an alternation policy. That is, it drains all fast path data before switching to the slow path. Then the software ring can preserve global packet order. And as a result, application can call a single receive API and receive packets in order regardless of the actual data path they used. And finally, I want to share some highlight evaluation results in the CEIO. We implemented CEIO on NVIDIA Bluetooth 3 SmartNICs using both DBDK and RDMA frameworks. And all experiments are conducted under a 200 gigabits per second network setting with two workloads, small RVCs and bulk file transfers to represent CPU involved and CPU bypass flows, respectively. And during the evaluation, we make the following observations. First, CEIO consistently achieve higher throughput across all settings. And in some cases, we observe up to 2.5 times throughput improvement compared to the whole CC and sharing. And second, CEIO significantly reduces the LLC miss rate. This validates the effectiveness of the credit-based flow control in avoiding the cache overflow. And the third, CEIO can outperform under various network conditions, whatever under the dynamic flow distributions or under network burst cases. And we also evaluate the effectiveness of CEIO. For the first pass, as expected, delivers line range and line range throughput, and additionally, the slow pass also performs efficiently when the message size are large enough, for example, more than the 4 kilometer byte, and its throughput is within 22% of the fast pass. And we also test CEIO under high fan-out scenarios where flows change rapidly. We observe CEIO maintains stable throughput when the number of active flows is moderate, and when the concurrent flow number becomes too high, for example, larger than 1K flows, throughput drops, revealing a scaling boundary. Okay, well, that is all the content for this presentation, and we would like to happy to answer any questions. Thank you very much for your attention.
Thank you very much. Any question?
Yes, hello. Isn't it just DDIO which is wrong, right? So you circumvent all this way of walking to the LLC. Shouldn't we have just a better design for the way DDIO works? Or?
You mean, can this design work with the DDIO components?
No, I mean, so you're trying to prevent the LLC from being overwritten, but shouldn't we more manage from the NIC the LLC? What is your thinking on that?
Okay, I see. Maybe, allocate more space for the LLC is always a solution for a system. And our assumption is the LLC space cannot be expanded or inflated very much. So I think that is the basic assumption for this work.
Okay, thanks.
Okay, thank you.
Any other question?
I have a question about the elastic buffer. Because you use the onboard DRAM to do the elastic buffer, but DRAM is very expensive. Why didn't you use the on-chip SRAM buffer? Thank you.
Okay, I see. Actually, with the elastic buffering, the goal of this design is try to, mitigate the network burst and wait for, the rate limiter to be effectively. So, actually, that is the one backup mechanism for the end-to-end system, and we do not really want to rely on the DRAM because, the DRAM is much slower than the SRAM, right? But that is the implementation problem for me, for us. For example, when we use the Bluefield 3 SmartNICs, we can only attach the DRAM space instead of the on-NIC memory. So for another platform, if we can attach or use the software to control the SRAM space, I think the performance will be much better than here.
Thank you.
Yeah.
There is time for another question. I'm actually curious about one thing. So now the driver, if I understand correctly, has to check 2 rings. Is there any overheads, apart from a PCI Express transaction on checking the additional ring, is there any additional other overheads or some specific checking that you might do for race condition, I don't know, or that your driver has to do?
You mean how the user use our drivers in the real system, right?
Yeah.
So, actually, we expose a receive API for the, the driver is not a kernel space one, just a user space library. For example, like something like the DBDK-based system, just expose several APIs. And the most implementation result for us is the receive API. So if you are a user, just replace the receive, maybe the DBDK receive or the socket receive with our API, and the user thread needs to operate several cycles for our programs to handle the different rings. Yeah.
Okay. Then thank you again.
Thank you.
Okay.